Welcome back to Kinetics. In part 5 of this unit, we're going to be talking about integrated rate laws, specifically for first order reactions. Let's get started. Now, first of all, the rate laws that we have been talking about have been called differential rate laws. When you just say the generic term rate law, you're talking a differential rate law, and that something like rate equals k times a relates rate as a function of concentration. If I increase the concentration of a, then that will increase the rate of the reaction, or decrease the concentration, that will decrease the rate of the reaction. But an integrated rate law, as in if you integrate a differential rate law, that'll do concentration versus time instead of concentration versus rate. So we'll use these laws to predict concentration of a reactant at a given time. If it's been 3 minutes, now what's the concentration of A? If it's been 4 hours, now what's the concentration of A? Or also the time required for a reactant concentration to reach a certain level. So how much time is it going to take to get A to half of what it was when we started, or to get A down to 2 molar instead of 6 molar where it started at? So that's what the integrated rate law is good for. So now we're going to integrate a first order differential rate law. So here's my first order differential rate law, that is rate is equal to k times a, or negative delta a over delta t. Remember, a is a reactant, that's why it's negative delta a, because a is going to be losing concentration over time. Now here's where the calculus comes in, and if you're good at calculus, you can just integrate rate equals negative delta a over delta t. But the College Board doesn't really care that you know the calculus, just that calculus has been done to this reaction, and when we did calculus to this reaction, we end up with the natural log of a at time 0 divided by a at time t is equal to k, that same rate law constant from before, times t. T is a time here, how much time it takes to get from a certain one place to another. So that is a first order integrated rate law. Put a box around it, circle it, star it. You're going to have to memorize this formula. That is the formula for a first order integrated rate law. So it doesn't really matter that you did calculus to that differential rate law, just that it has been done, and here's the new reaction. So now I'm going to do a little bit of deriving. I'm going to kind of rearrange that equation a little bit. According to the rules for natural logs, ln AO over AT is the same thing as ln AO minus ln AT, and that equals KT. If I subtract ln AO from both sides, I have negative ln AT equals negative ln AO plus KT. And then if I divide both sides by -1, I end up with positive ln AO equals positive ln AT equals positive ln AO minus KT. And here is another form of the equation. So all I've done is rearrange the reaction in purple to turn it into the reaction in red. The reason why I want this rearranged is because it's kind of tricky for a lot of people to look at natural logs and try to figure out how to use a natural log. So I kind of memorized both of these versions of the equation based on what I'm going to need for my math. Now looking at that equation, hopefully you notice it's in the same form as the equation for a line. That is y equals mx plus b, the equation for a line, meaning that ln AT is the y-axis. T, or time, is the x-axis. M, or slope, is negative k, so the rate law constant is the slope, and the intercept is at ln AO. So we can make a graph out of this. So just before we're gone, AO is the initial concentration of A. AT is the concentration of A at time equals, didn't do that right, T, and let's see, T is time. Just so we make sure we're clear on all of our variables, and then K is just the rate law constant that we've been dealing with all this time. So now, let's graph it. if we had a graph of just concentration of A versus time. A starts high because it's a reactant, and it's going to get lower and lower and lower as the reaction proceeds. But at some point, the reaction is going to come to equilibrium, so it's kind of a curvy line, probably prettier than that curvy line. Let me try it again. But starts high, ends low. Ooh, there we go. And it probably doesn't start before the axis starts, but you know, something like that. But when you graph the natural log of A versus time, it starts high again, but it goes straight down in a straight line. So this goes along with ln A t equals ln AO minus KT. So the slope of this line is equal to negative k. Notice it's a negative slope, the line's going down. We've got time on the x-axis, we have the natural log of A on the y-axis, and we intercept the first point on the line is where ln of A is at the initial concentration, or the beginning of where A was. Alright, so now let's look at half-life for a first-order reaction. Half-life, denoted by T with a little 1/2, is the time required for the concentration of the reactant to decrease to half of its original concentration. So it's not how much time, well, it's not when the time is in half, but it's when the concentration is in half. So if I started with 100 grams and in 2 hours, it took me 2 hours to get to 50 grams, then 2 hours is my half-life. So starting with that original integrated rate law, ln AO over AT equals KT. Starting with that, I'm going to derive an equation for half-life. And so what I'm going to say, when the concentration of A is half of what it was initially, then AT is equal to 1/2 AO, because A at time t is half of what it was at time 0. So plugging that in, I have ln AO over 1/2 AT equals KT half. And I'm denoting T as T half because I want to make sure we're talking about not just some random time, but the half-life time. So I made that AT, but it should be AO, 1/2 AO. So now I'm going to say AO divided by AO, that's going to cancel out. And 1 divided by 1/2 is the same thing as 2. So I end up with ln of 2 equals KT half. If I divide both sides by k, I end up with ln of 2 divided by k equals T half. Well, the ln of 2 is a constant. ln of 2 is always the exact same number, and that is 0.693. So for a first order reaction, half-life is 0.693 over k. So this is your half-life equation that you get to memorize for a first order reaction. Now what's important about this half-life equation is that the A's completely canceled out. So this is not at all dependent on the concentration of A. It's not at all dependent on the concentration of A. So it has nothing to do with what A started with or what A ends with. It's just 0.693 over what the rate law constant is. So that's something to keep in mind. Let's look at an example where we can use those formulas. So we have an equation, R makes P. The reactant turns into product. It's a first order reaction. Therefore, rate equals K times R to the first power. And RO equals 0.3. Notice that there's no unit here because there's brackets there. Since they have a bracket, the bracket makes an assumption that the unit is molarity. So using a bracket makes the unit capital M redundant. But sometimes you want it in there, just so you know that the concentration is in molarity. And T half is 20 minutes, that is the half-life, how much time it takes to cut R in half is 20 minutes. So the first thing we're going to do is determine the rate constant K, and the equation that we just solved for is T half is equal to 0.693 over K. So I know the half-life is 20 minutes, and 0.693 is a constant divided by k. So then I can rearrange and multiply both sides by k and divide both sides by 20 minutes, and I end up with k is equal to 0.693 divided by 20 minutes, which is 0.035 per minute. 6.693 does not have a unit, the natural log of k. It's just a number, because remember it was AO divided by AO and they canceled. So it's just per minute. That's my unit for k. So now, how much R is left after 60 minutes? What is the concentration of R once the time has been about an hour? I'm going to use the integrated rate law to relate time and concentration instead of rate and concentration. And so we have ln of AT equals ln of AO minus KT. So how much R is left? That's going to be the concentration of A, and in this case, A is just R, because R is the reactant that we're talking about. So we'll make this R, just so we're making it particular for the equation that we're looking at. So the ln of R at 60 minutes, at time is equal to 60 minutes, make that prettier, is equal to the ln of R at 0 minutes, that is 0.3 molar, minus K, that is 0.035 minutes negative 1, times time, which has been 60 minutes. Hopefully you're seeing that the minutes negative 1 and the minutes are going to cancel out. And so 0.035 times 60 is 2.1, and the natural log of 0.3 is negative 1.2. So I end up with ln of R at 60 minutes is equal to negative 1.2 minus 2.1, which is negative 3.3. The ln of R is equal to negative 3.3. So the inverse of natural log is e to the power of. So in order to cancel out the natural log here, I'm going to take e to the ln of R, and the e and the ln, those cancel out, equals e to the negative 3.3. So on your calculator, inverse natural log is a little e, and it should be just above the natural log button. And so R is equal to 0.037 m. There we go. Now, how much time is required for the reaction to be 75% complete, or 25% of the initial amount remaining? I put that A there just so I could remind myself that K is equal to 0.035 per minute, just so I wouldn't forget it. So how much time is required? Again, we're looking at the integrated rate law. I'm going to use the other form of it this time because I'm finding time. It doesn't really matter. You can interchange whichever form of the first order integrated rate law you like. I like this one when I'm solving for time because essentially it's in a format that I can already find time, and I like the other one when I'm solving for concentration because it's in a format to already find concentration. So let's just plug in what we know. The natural log of R at time 0, that was 0.3 molar, and now it's 75% complete, or 25% of the initial amount remaining. So 25% of 0.3 times 0.25 is equal to 0.075. 25% of the 0.3 is remaining. That's 0.075 molar. Equals K, which we've already solved as 0.035 per minute times T. So what we're going to do is divide 0.3 by 0.075, and that is 4. So we have ln of 4 is equal to 0.035 t. And so we'll divide both sides by 0.035, and t is equal to 39.6 minutes. All right, and that's how you use the integrated rate law for first order reactions and the half-life for first order reactions to solve for time or concentration. Join me next time when we look at second order reactions and zero order reactions.